I'm also going to tell them that if they want to pose any questions and if they need any
clarification
or assistance with English, I can help them to pose the questions. I don't think so, because in Portugal normally people do understand English. Like it.
Not very fast English, but English. But
I'll try and be slow.
Yes. Vamos então iniciar esta apresentação. Queria antes de mais cumprimentar todos os que estão aqui presentes e quero antes de mais cumprimentar os nossos convidados. A professora AnnaLisa, da Escola de Arquitectura da Colômbia Britânica, à Embaixada do Canadá, representada pelo Eurico Nobre, a quem agradeço todo o apoio incansável prestado, permitindo de facto a realização deste evento e a vinda da professora AnnaLisa. Quero também, peço desculpa, esperamos mais um bocadinho. Este evento faz parte de um conjunto de iniciativas que têm como objetivo maior potenciar o uso da madeira na arquitetura portuguesa, que passa, antes de mais, pelo aprofundamento do conhecimento em torno da sua utilização do ponto de vista técnico, quando associada à construção de uma forma arquitetónica. Sabendo que Portugal foi, outrora, detentor de grande habilidade e conhecimento no uso da madeira, sobretudo na construção naval, não podemos esquecer o grande engenho depositado na construção de edifícios da Baixa Pombalina após o terremoto de 1755. O nosso objetivo é recolocar Portugal como referência na utilização da madeira e, para isso, temos necessariamente que informar a nossa prática, enquanto arquitetos, com o objetivo de ajustar cada vez melhor à circunstância geográfica, climática e florestal do país. E ainda, a interação entre produção arquitetónica e tecnologia na construção, com produção de formas que nos transferem para ambientes diferenciados, necessitam de uma abertura da nossa prática às novas tecnologias de produção que interagem cada vez mais com a construção de edifícios. Nesse sentido, iniciamos este caminho com a criação de uma unidade curricular opcional denominada Construção de Arquitetura de Madeira, que termina este ano letivo com a vinda da professora AnnaLisa Meyboom, com a conferência intitulada Innovation in the Architectural Language of Wood. Quero então agradecer à professora AnnaLisa por ter aceito prontamente este convite, agradecer à Embaixada do Canadá por todo o apoio prestado e agradecer à Faculdade de Arquitetura da Universidade do Porto pelo acolhimento deste evento. Dou agora a palavra ao Eurico Nobre, a quem agradeço.
Eu vou falar em inglês, não se preocupe, se não se importarem, só para a AnnaLisa compreender. Portanto, eu escrevi 3 parágrafos, não me quero alongar muito, não tenho muito para dizer, não sou um expert em arquitetura, portanto só vou dar aqui as honras da casa, mais nada. Cara Ana, em primeiro lugar, muito obrigado. AnnaLisa, membros e direção da FAUP e futuras arquitetos. First of all, on behalf of the Canadian Embassy, I would like to thank FAUP for inviting us to this conference today. It all started last year when Anna reached out to us seeking for assistance to bring the exhibition First to Forests from the Canadian Centre for Architecture, CCA. You might be familiar with CCA, has half of the archives of Cisa Vieira, to Porto. We haven't succeeded in bringing the exhibition so far, but we haven't given up on it. There is so much to say and to write about Canada's close ties with wood and timber construction, as evidenced by its maple tree leaf emblem. Canadian architects have been contributing substantially for the development of timber design and architecture at various scales worldwide. There are several examples of groundbreaking Canadian timber projects and drawings that range from temporary installations to high-rise wooden structured buildings. The 18-story residence at University of British Columbia Now the tallest building in the world with a primarily wood structure is one of the examples, or the prime example. However, I would just like to emphasize that wood continues and will always remain one of Canada's favorite building materials, hopefully. We invited Professor AnnaLisa Meyboom to come to Porto to share a bit with you on how wood can be an excellent material for construction in terms of sustainability and precision in the details. Professor Meyboom teaches architectural structures and design build courses. Correct me if I'm wrong, I took it from your biography. Research studios and advanced structures and computing seminars at the School of Architecture and Landscape Architecture at the University of British Columbia in Vancouver. I'll leave you now with Professor Meyboom. I hope you enjoy her presentation and have a nice and pleasant conference or symposium.
Thank you very much. Thank you very much, Anna. I'm very pleased to be here for the country, and there were several of us that were vying to come here when I won, so I'm very happy to be here and present. So, looking at Is that better? Good? Just a little bit. Like this? Can you hear me well? Okay. I'll try and talk slowly. So, the topic of this lecture is the language of wood in architecture. And I'll tell you a little bit about where I come from and why my region might be a place that you would design in wood, just to give you some context. So this is the School of Architecture and Landscape Architecture at University of British Columbia. This is our campus. It's in Vancouver, so we are a little bit out on the peninsula from Vancouver. And Vancouver is known for its position relative to nature. So we have the mountains in the background, and we have a lot of forests near the city, and then the city itself is quite dense and has a lot of high-rises. Very different than Porto. This is the university campus. This is the main mall, and this is, our university is ranked in the top 20 public universities internationally. We're funded by the government. It's also ranked in the top 40 universities overall internationally. So it's quite a well-respected university globally as well as within Canada. We have 55,887 students on our Vancouver campus, and 16,000 of those are international students from 156 countries. So we have a very international student population. We do a lot, it's a research university, so we do a lot of research, and we have 207 companies that have spun off research that UBC has done to date. This is our architecture school students, so it's probably very similar to what you see here. We have kind of a lively, diverse student population. In the School of Architecture and Landscape Architecture, we have 325 students, 25 faculty, and 7 programs. And those programs consist of mainly the Bachelor of Environmental Design, which is our undergrad program, a Master's of Architecture, which is where I teach, a Master's of Landscape Architecture, and a Master's of Urban Design. And we also have some smaller master's programs that are more specialized. So that's the breakdown of the school. Our research areas that are of interest generally are housing and society. So when we look at housing generally, and I'm sure that you guys have kind of similar research areas, it seems like. We have form, aesthetics, and practice. This is showing you an installation from Matthew Sewells, who was growing a landscape that is reversed. We have Bill Packett, he's one of our kind of contemporary architect artists who does a lot of public space design and installation, looking at and he's always working around infrastructure. And then we have design and construction futures, which is more the area that I am talking about today. This one here is a different project by Joe Damon, who is looking at constructing out of natural growing materials. In this case, it's a mushroom. So he uses that similar. It's a bit, I guess, a bit similar to your cork, except that in this case it's actually growing. And then we have Blair Satterfield from research who might also be interested in it. He's another one who works sometimes in wood. He's also interested in looking at waste products and how you can reuse those waste products. So his view on the wood in this research was about how to reuse the wood that comes from houses that decay down. And so he's right here, he's looking at a process of kind of fabricating that zippers the wood into different types of shapes. And then we have healthy and resilient communities. Adam and Bryce found that this is looking at more environmental controls. His research here is looking at cooling, radiant cooling through running cool pipes through walls. So you don't have to use air conditioning, you can reduce energy use by running cold water through walls and having the radiant cooling affect the space. So that might also be relevant in which is where it's hot. Not so relevant in Denver, but he was working in Singapore at ETH prior to that. So we also have Case Lockman, who's looking more at living breakwaters and dealing with water control with climate change through natural processes in landscape. And he's from our landscape architecture side. So generally, when we look at how we go about kind of doing this work, we focus a lot on collaboration. So we have a lot of collaboration with other faculties and other parts of the school, which I think is relatively suitable for architecture, environmental design schools. And then we have collaboration in terms of the landscape and architecture, which is even offer a dual degree where you can do a master's in architecture and a master's in landscape architecture together. So, is this working?
It's not that we can. Yeah, now it's working.
Okay. Can you hear me now? Okay. So the collaboration is, we collaborate outside in other disciplines, but also within our school, we have the architecture and landscape architecture together. And so this is a project that is being done by both students and both working together. We also have a lot of community, we work in the community. This is an installation of our undergraduate students. They created a big board and everyone gets to go and put on sushi costumes and lie on the board as a kind of a public, it's a fun public installation. It was a competition that they won for the local festival. And so that was fun. And then we also have, we do work with our First Nations. This is a path making workshop in terms of kind of integrating with our First Nations community, which is a big kind of cultural aspect of Canada and how Canada operates. We also run a design build program, and we build like full-scale buildings in different, it's usually in a camp. This one is Gambier Island. It's a camp for children to go and learn about the environment. And so they need buildings, but they don't have too much money. And so they give us money, we get donations for materials, and then the students design and build the buildings that they need. And these are usually in forested locations, kind of relatively remotely from the university. So that's kind of the way our program works. And this is University of British Columbia. This is the building that Yuriko was referring to. This is an 18-story wood building. It's Brock Commons. It's a residence hall. And you can see it here. It's under some construction. And that's by a local architect, Acton Austria Architects. So they are interested in kind of innovating in wood. And in fact, there was a program that's called Wood First in BC, which means you have to build in wood unless you can prove that that there's some reason why you can't build in wood. So it's so wood oriented that first you have to consider wood, and after you consider wood, then you can consider something else. Partly it's because we have a large forest industry in British Columbia, and partly it's an environmental concern. So we'll talk about that a little bit more, but this is the interior of that building when it's under construction. Now it's all covered with different interior, like drywall and the inside, so you can't see this, but you can definitely see it's made of cross-laminated timber and columns. The core itself is concrete. We're in a very high seismic zone along the Pacific Rim, and so far they're using the core as concrete. This building was built to prove that it could be done, and it was built very quickly and very inexpensively for the purposes of making the case that you can build these buildings in wood. And then for this building, we didn't challenge the codes because we wanted to do it quickly and have it there. So in the future, there'll be more, when the codes evolve a little bit more, there'll be more aspects of the building that could be wood, right? So the core and the fact that you could expose more of the interior wood. Right now, it's mostly covered with drywall. So our codes are also, I think they're more suited to a wood, building in wood, but in terms of these tall wood buildings, it's still experimental. And so we are doing it at the university as an experiment. And now that we've proven that it can be done, then it can be taken elsewhere and in Canada and also in the city. Right now, the limit on wood buildings is 6 stories in Canada. And that's mostly light wood frame, if you guys are familiar with the light wood frame system. So in our region, there's a long history of building in wood. This was, especially in architecture, looking at regionalism and modernism, if you guys are familiar with that kind of movement. So the idea that they were modernists building, but in specific regions. One of our most famous architects who built in this style was Arthur Erickson. And you can see this is the typology that he built. Very much a lot of wood and then some glazing. Glazing was it was single pane and was framed into the wood. And the reason we can do this is because we have a very moderate climate. It's 5 degrees in the winter in this area and then maybe 25 degrees in the summer. The code does not allow this anymore, but this is kind of the history of architecture in our region. And so then nowadays we have more innovative work going on in this region probably than any other region in Canada. This was the Richmond Olympic Oval, and that is one of the main buildings for the Olympics, the Winter Olympics that we had in Vancouver. Fast and Epp are the engineers who are a very innovative engineering company that supports the architects in our region. They come into the architecture school a lot and they do joint critiques. They support competitions that we do where the engineers and architects work together. So they're very keen on architects and engineering working together early while they're in school, before they even get out of school. So that's the Fast Epp, and then Canon Architects are another local architecture firm. This one here these are giant Glulam Arches running this way. They're actually in this shape here, and they have these are like skates, considered like skates, and they have a steel part, and all of the services are hidden within those major elements. And going in this way are what they call a wood wave, which is 2x4 arrangements that are just nailed together, and composite arches going the opposite as well. So the whole thing is wood. This I particularly liked. One of the architects who does the most innovative work in Canada is Pat Cow Architects. If you guys are maybe not familiar with them, it's worth looking them up. This was a competition entry they did for Korea. This is the same engineers that they're working with. They didn't win the competition because they spent too much time on the structure and not enough on the program, is what Pat said. So, but it's a beautiful project. It's meant to be, this is the exterior of it here. So it's a ruled surface. The curved surfaces are made only by straight lines. And then it's meant to, it would have a concrete composite surface on the top of it. So we'll be working compositely with some concrete in this case. And the whole thing can be done with no specialized labor in this case, no specialized fabrication equipment, and all off-the-shelf wood. And so that's that was an experiment looking at that kind of process of how that might be done. This one is actually built This is the Temple of Light. It's a much more complicated fabrication process, and it uses a lot of parametrics in its design and also in its It's in the interior of British Columbia up, and it's a yoga retreat, also by Packhouse Architects. Bing Tom is another one who is famous for using wood. Unfortunately, Bing Tom just passed away, but he worked internationally in the States, also in Hong Kong. And he's from our university. And you can see him standing next to one of what we call a paralam column, which is a wood engineered column with a nice cast connection to the base. This was built in Washington, D.C., because Canada is always having a fight with the United States. And what Bing Tom says is like, he's going to take the wood to the United States and put it in their capital. So he did that in a building. And so we gave him a wood design award for that. Anyway. And this is the Grandview Heights Aquatic Center. So this is another, we use wood in our aquatic centers, in our swimming pools. This one is actually working in tension. So there's no steel in this. It's the wood itself that is doing the tension in this structure. So it's a hanging catenary made of wood, which I thought was very innovative, because we usually use wood, in compression or in bending, but not in tension. So this is pure tension structure, and so that's why I thought that was great. Again, we're using the engineers Fast and Ep and then HCMA architects, but we do have other engineers in British Columbia, and I'll be talking about them sooner or later. And this is just another example of kind of more free-form wood that's being built in British Columbia. And this is looking at the Van Dusen Gardens. So it's a gardens that you can visit, a botanical garden in Vancouver. Again, you can see the same kind of language that we're seeing in the other projects, where we have the columns and then the wood structure. This is a rammed earth wall on the right side, if you guys are into that. I think our students are. I don't know. So then, what else is happening in Vancouver? We have this emerging startup culture in wood architecture, and this is a really interesting development. Several of our companies who are kind of foremost in architecture and engineering have been bought up by a large startup in the United States called Catera. And what they're interested in is mass producing housing and prefabrication. So what they're doing is they're taking the whole supply chain from all the way to the design to the build, and they're putting it into one computational process through building information modeling. So when you design the building, all of the fabrication is already programmed. And then you have a high certainty of the cost of the building because they take care of everything. So they integrate the whole process all the way from design to build. So this would be likely, I think, what's coming for us in the future, where you have that whole integrated process. That may be highly problematic for architects, because where do they fit in? And they get hired by these companies. I think that's a really interesting discussion. But this is what, when you look at Todd Dalland, and he's looking at what is hip now in architecture, is this kind of prefabrication, designing mass housing, owning a factory, integrated design office, prototyping shop, and marketing and sales, securities, industry, business, lawyers, and accountants, intellectual property, and patents. This is all integrated because you're designing the whole fabrication system. So this is, as I say, this is what seems to be up and coming in Vancouver. Also in Toronto, if you've heard of this project, this is Google's Sidewalk Labs. It's extremely high kind of profile project in Canada. It's highly contested because of the privacy issues. But what they're proposing is that all of their housing will be prefabricated and more efficient. So the same idea as we saw previously, they're going to integrate the whole supply chain and make their prefabricated units and plug them in, and therefore housing is going to be cheaper and more affordable. So that brings us to this statement here. The question is no longer whether digital technology is a good or a bad thing for design. It is rather about the direction architecture is taking under its influence. Confronted with a series of technological innovations, the only certitude we have is that the change that they are bringing is profound. It may prove as radical and enduring as the transformation that gave birth to the architectural discipline at the beginning of the Renaissance. And so my question in terms of what is happening then is whether or not can actually, what kind of change this is bringing, and whether or not it will bring kind of the utopian ideals to architecture. These are prefabricated houses that they sold in North America in 1904. So in the early stages of the 20th century, these were very popular because they didn't have enough labor. So they would ship the entire house, it was all wood, and they would ship it to site and build it on site. So this is not a new kind of concept, but it went out of fashion because after World War II, labor came back to the country, and so they had labor, and they didn't need. This is more for the settlers who came to Canada in the first place. But when we think about what prefabricated housing could be now, we have all these. We have a kind of a robotic assembly process, and we have this idea of this technology is now going to kind of influence what's going to happen in architecture. And so I think it's worth considering what that means for architecture and what that means for how architects operate. The other thing that we might want to consider is the environment. So one of the other pressing issues that we need to deal with is how we deal with the building in what the materials we use and how sustainable are those materials. And that's where wood has a very large advantage because it's a renewable building material. So you replant a tree with the new seedlings, and in 50 to 100 years, you'll have another tree available for consumption. This is really key, and this can be sustainable if you do it with the sustainable forest management practices. And so I think that's key to mention is that if you just take down every tree, that's not a sustainable practice. But if you replant the trees, then it's almost like you're farming trees. You keep using the material. So in Canada, we have zero rate of deforestation right now. Anything that we harvest for trees, we replant. And this has been constant for this for several years. We also, 94% of our forests are owned publicly, so they're owned by the government. And so the government has control over who can harvest, when, and how much can be harvested, and that they have to be replanted. So that gives us an ability to kind of think very long-term about how we're using the wood and how the forest is being harvested. And we say less than 1% of the amount of the forest in Canada is harvested every year and replanted. So this is, in Canada, these are our forests. We have managed forests and unmanaged forests. Managed being that you can harvest them and then replant them. Unmanaged being that we haven't harvested them yet because there's enough that is harvested, we don't need to. And then I put this little here, which gives you a context of the size of the forests. So that's Portugal. I've put it into, I think it's in Quebec right now. And so that gives you, so Canada is very large, and we have a lot of forests. And so when we say we harvest, a certain amount of it and we replant it, we have a lot more work for the next year and the next year and the next year. And that's similar to some other countries like Russia and Germany. So this is just looking at the sustainability of how this works in terms of forests. This is a little bit complicated, this graph, but what we're looking at is if you have an unmanaged forest, you have, that's the upper line there, and a managed forest you're harvesting, right? And then you're regrowing and you're harvesting and you're regrowing. So that's what happens with the cycle of how much, in terms of typical carbon sequestration, meaning how much carbon is stored in the forest. So we're trying to store carbon because it doesn't get released in the atmosphere then. So when we see this is a forest fire that happens, it burns the forest and it releases the carbon. So we are also trying to avoid kind of forest fires. But this is only one part of the story, because when you harvest the wood, then you store it in a building. So this building, when we build things out of wood, we're storing the carbon in the building. So then when we also plant the forest, then we store more carbon in that forest growing. So the idea is that what you're doing is you're improving the carbon impact because you take the forest, you put it into a building, so you're keeping it in the environment. Then you build another forest which stores more carbon. And so the more you build with wood, the more carbon you store in the environment. So that is very helpful in terms of reducing the impact of greenhouse gas emissions. Wood itself is 50% carbon by weight, and it's also stored indefinitely, as I and 1 cubic meter of wood stores 1 ton of CO2. So these are all reasons why we might want to be interested in building things out of wood. In North America, a typical North American wood frame house, which is the light wood frame, stores 28 metric tons of carbon. And that equals the carbon dioxide generated from driving a car for 7 years. So we also, in terms of using a log, we use 98% of the log in different wood products. So whenever you take down a tree, then you don't waste that tree. Everything is used out of the tree. It's partly good business practice, and that actually is a good environmental practice as well. And then we're looking at wood in terms of comparing it to different materials. We're looking at total energy use, greenhouse gas index, air pollution index, and solid waste. You have an advantage when you're using wood in all of those aspects. So that's why you guys might be interested in building more out of wood, and why we're, as a global kind of population, we should be more interested in building things out of wood. So my personal interest in terms of all of this as a person doing research in architecture is how might digital design and fabrication change the language of wood architecture. So we've built historically, you've built many years of hierarchical wood structures where you have beams sitting on joists, decking, and then you have joists, and then you have beams, and you have columns, and that's very linear and hierarchical. But there is a huge potential in wood because it's highly malleable and easy to machine. So when we think about how we can make forms in architecture, how we can make these digital forms that we might be interested in, then we can look to wood as a potential material that can do these types of forms. And when we look at these kinds of projects, it can also be structure, enclosure, and finish. So it can be multi-purpose and do many things for us in architecture that we'd like it to do. And in a way that people feel very compelled by. I think that there is in most cultures this kind of affinity for the naturalness of the material. And it has a very nice reflection with the light and carries, and you guys know from this building here, that it can be a very pleasant environment. So one of the greatest advantages then is that we have of these digital tools is that we allow the integration of the disciplines to come together within the digital platform. And I think this is a really significant aspect. And that means that the connection of, and this is a quotation, the connection of digital fabrication and computation enables the immediate programming of production data and directly links the design with the making of architecture. As a result, the architect can fully control the construction process down to the smallest detail. So this changes the role of what an architect does and who's fabricating, right? So when we think about, we're drawing details, right? We're thinking about those details. In the case of these, we're also making the detail, right? If you are actually controlling the fabrication process, you are actually not just drawing anymore as an architect, you're actually building. So that means that it changes this kind of historic relationship we have with drawing, right? Especially when you're the one who is operating these systems. So we have this kind of computer-aided design, finite element analysis, and computer-aided manufacturing that are now all playing a role in architecture. And I'm not talking too much about this in this lecture, but the analysis, when you have these very advanced tools, and I'd say that we're coming along in architecture, we haven't quite got there yet. But Grasshopper has an integration of, environmental analysis and structural analysis coming within it. And so when we can integrate fully these types of all these processes, then you collapse the disciplines, right? Then the disciplines all are working on the same software. They're working in the same program that everything, whenever you're an architect and you change something, you can see what it's doing to the structural analysis. You can see what it's doing to the airflow. So that gives the architect a bionic ability, I call it. And and not only that, but then we can feed into our computer-aided manufacturing. So when we change something, and we can see that what's happening within the fabrication is feeding back into the analysis, and we can cycle, and it gives an architect a better understanding of what they're doing, and also better control over how things go together. So The fabrication processes, when we look at them, we have subtractive, which is the laser cutter, the CNC, and the Hundinger, and the additive, which is the 3D printer. But the one that's actually the most interesting to me is the industrial robot. And you can do so many things with that because it can be additive or subtractive. So the question is, what might we want to do with wood if we could? And this is a project I'm showing by FISAC, who is doing post-tension beams, which is a kind of innovating in concrete in the kind of the early days of post-tensioning of concrete. And here's another project that we might think about with wood. What would this be like? This is a Toyo Ito Karamigahaki, excuse me if I pronounced that wrong, funeral home. It's kind of this undulating surface, this shell surface. But one of the interesting things to note about this is that this was originally built out of wood first. So before, in order to form the concrete, you had to build the wood structure. So my question is then, why would we build the concrete? Why don't we just build it out of wood? And so this is the formwork for that particular structure. So what are we looking at in terms of research? So these are all the possible future directions that I'm interested in for architectural research in wood. Challenging how curved it can be, challenging what forms it can take, challenging how thin it can be, challenging how strong it can be, and challenging its weaknesses in terms of its ability to be exposed to weather and biodegrade. Some of these aspects are coming, when you see in the research in the last few years, we're seeing a lot of research in terms of how to leave the wood exposed with some very innovative materials. But what we're working on are these two here. So challenging how curved it can be, and then challenging what forms it can take. So we have a group at UBC called the Wood Design Chair. It's a group of faculties, including the School of Architecture and Landscape Architecture, Wood Science, Civil Engineering, and the Center of Advanced Wood Processing. And we are together in this group that is the Wood Design Chair. This particular research that I'm going to explain to you right now is done by myself, Ian McDonald, who was at Center of Advanced Wood Processing, Oliver Neumann at School of Architecture, Thomas Tannert, who's cross-appointed in Civil and Wood Science, and then our fantastic students who have now graduated. And so the three kind of interesting forms that we're interested in looking at were all surface structures. So the idea of a kind of a surface to be the expression as well as the structure. And we looked at the folded plate, the rule flap planes, and the double curved surfaces. So this was proof of concept research. And we started with the folded plate structure, which I think is relatively common, not common, but there are research projects in other parts who have also looked at folded plate structures. So we were interested in kind of an exploration. This is showing span in one direction. So this one here is just a kind of simple spanning structure with different wall configurations, which help you with the lateral stability of the structure, as well as dealing with the stability of the walls. In certain cases, for example, this P1 and then the DB1. Then we are looking at the same, so these iterations of structure are looking at one fold in the middle here, so that we start to create a kind of more of an A-frame, and then so that's the second row there, and then the specific fold conditions get more complex, and then the third one starts to kind of take on an arch shape. So there are many different forms that the folding can take. And then this was the material that we were looking at was our cross-laminated timber material, and we did this. This is our engineer looking at. We understand what the loading condition is in this case, and the loading condition is in this case, and what happens if then we change the loading to the form that we're interested in looking at. So we cut our element, and then this is an integrated process with the Grasshopper. So what she was doing was trying to integrate the structural analysis with the Grasshopper. And so the angles of the plates could then be taken to that. And then we have looking at the joints. So obviously, whenever you're, when you're looking at these kind of complex wood structures, one of the key aspects is how do you make the joint? So there are several investigations of how you could make the joint in these structures. So in our case, we settled on the third joint here, which is self-tapping screws going diagonally into our elements. And we have a prototype structure that we created, which is this made out of the five-axis panels, five-axis cut panels. This is before we had our robot. So these are looking at the techniques that we have. We had in the shop, in the Center of Advanced Wood Processing. So you can see here the students who are, this is our engineer on the right, our architect student on the left, working together to build the prototype. And then we have our kind of final prototype. So in this case, it's not a simple folding, but the folding is kind of changing angle at the base, getting more stable as it gets wider at the base, and then it's crossing, coming up to the top part. So this, when you start and you actually go to build these prototypes, then of course you realize all the ways that you could improve the way the pieces go together. In this case, when you see the lapping, in terms of how these pieces go together, this particular element here, these are very sharp angles that come together, but they slide relative to each other. So building the prototype helps you to realize that you need something that helps you place those pieces relative to each other. So this opens up a whole, when you're looking at how these elements kind of place together, what you want is some kind of notch that gives you the instructions for the fabrication within the actual build form itself, which is a kind of an emerging research area. When you actually use a robot, you can embed the instructions for fabrication within the pieces themselves so that they go together a lot faster. So that was something we learned from this particular installation. And then we went on to look at the second element, which was the ruled surface of the lapped plates. This lapped planes. This one we didn't do a prototype for it yet, but we could do that in the future. And so what we're looking at is trying to make a curved surface out of straight plates. So using the geometry, and we're looking at kind of cross-laminated timber in this case, because we're looking at, so we're saying, okay, well, when we use a longer plate, we make a more straight line, and when we use a shorter plate, we can make a curve through the use of those different types of plates. So that's the basic principle. But then you can use geometric complexity to change the what you would call the kind of the angle of those plates relative to each other. So as you kind of move that angle of what we call the directrix, then you allow more interesting forms that kind of open up, right, and then are more steeply curved at the bottom. And so not only do you're controlling this particular angle, but you're also controlling that angle. And so you'd think that what can you do with a flat plate? But it turns out you can do a lot of things with a flat plate that we don't currently think of, because like we say, we usually think hierarchically about wood. So this started to kind of get into the idea of what else can you do now. We did this research before we had our industrial robot, but you can also angle the edges of those plates, right? And you can start to think about how you might kind of make a more smooth surface just through cutting your plates at specific angles. So this opens up a whole other, I think it opens up a bunch of questions really about what else you could do. So we can see in three-dimensional form, because it's, I'm sure if you guys already use parametrics, you realize that as soon as you add one complexity and then you add another complexity, it very quickly gets out of control. So you have to try and limit the kind of the amount of complexity you add. But here we can see one generating plan curve, right? And then so that means they have a plan curve on the base, and this is two generating plan curves. So we have a curve up here and a curve down here. And then you can have multiple generating plan curves as well. But you can see there's, architects might have an opinion about this, right? Because at some point it becomes chaotic, right? So, but anyways, all this is meant to prove is to kind of look at what the possibilities are. And it seems like there are a lot of possibilities. So that's exciting. The third one, which I think we took the furthest of all of them, was the double curved surface. So this one here, when you think about how we're going to make this, there's a potential for machining something into a curve, right? You take a big block and you cut some part of it away. But I don't think that's very interesting because you waste a lot of material. So you're cutting out a lot of wood, and yes, we can recycle it and we can make it into MDF or do whatever. But it seems like it would be more clever if we could get it to follow the curve of the actual structure. And so that was the attempt in this research, is to say, how could we make this out of wood? Well, it turns out that they already make curves out of wood in the form of a barrel, which probably you guys make more barrels than we do. So I don't need to tell you how to make a barrel probably, but anyways, just in case you guys are not making barrels, this is how you do it. So you take a piece of wood and you cut it. They probably in the wineries don't cut it with a 3-axis machine, but you can cut it with a 3-axis machine or a 5-axis machine. It turns out you need a 5-axis machine. But so here's your pieces that you're making it out of, and in the case of a barrel, then they put tension ties in steel, right? So that's the principle of how it goes. And then what we're interested in doing is making double curved CLT. So that was the fun we were having. And so we basically take the barrel shape and we apply it to a large structure. And to do that, we need to cut our pieces of wood at a very specific shape. So the shape that we cut them at depends on the global geometry of the project. So in the terms of we have here, we're analyzing the geometry. So if we have a cylinder, for example, here, we have a curvature in one direction, right? And when we look at the torus, we have a curvature in one direction and a different curvature in the other direction. And when we look at the sphere, we have a similar curvature in the two directions. So those are the kind of the basic geometries that we're interested in looking at. Now, what we're doing here is using the elastic bending radius of the wood. So wood bends, right? And you can bend it within a kind of what we call the elastic bending. Does anyone know what I'm talking about when I talk about the elastic bending radius? No? I know it's, so I can bend wood without failing it, right? To a certain extent. That amount of bending depends on how thin it is. If it's very thin, it bends a lot. If it's thicker, it bends less. And I can still use the wood because it's still working structurally if I bend it within its natural bending radius. So as I want to have a larger structure, right, I can use thicker members because it bends less. And if I want to have a tighter structure right here, I use a thinner member because I can make it bend more. And so we can adjust or tune the thicknesses of the laminations according to how much span I want. In a building, typically you want a very large span, so you can use a thicker material. And that's the principle of this. So now we're making barrels, but we're making them into buildings, and then we might need to connect those pieces. So the question again becomes, how do we join these pieces? And this is not resolved, this is just a suggestion. We can maybe have some collaboration and resolve this problem, but we haven't done that yet. So there's different ways you could go about. So our self-tapping screws, like we used in the other example and has been used by ICD in Stuttgart on several of their projects. And then we have also a lapped joint here with some crossing screws, and then an infill panel, an infill piece that goes across. So there are some potentials for making this connection. This is a shell structure, so you have in-plane forces, ideally, but probably you need to design a little bit for out-of-plane. We could also do it with some more these are NAP connectors. They're very expensive, they're proprietary, so not as ideal in our minds. And then there's also kind of aspects where you might be able to glue it. This is similar to the connections you see in wood whenever they're trying to connect like standard lumber, and they just make a very large surface area and apply glue. and that allows you to kind of have the stronger connection within the joint than you do with the wood itself, and therefore that's how that one works. So there's a possibility of also doing that. Again, you can see it needs advanced machining because you have plates at angles and then you have other plates at angles. With a robot, it's no problem. So we are looking then in terms of integrating this with our engineering process. It's a relatively advanced structural engineering problem because we don't want the engineers to have too easy a time of it. So we're looking at a shell structure that has laminations in opposite directions and has several layers of them, and then we want to apply some kind of load to that and see what's going to happen. So this also is, when we're looking at that, we tried to integrate this process in terms of surface generation and creating a mesh within that, and then integrating that with the within the engineering software, so that we have some kind of way of moving that back and forth between the architectural and the engineering software. So this is, you can see us making the prototype. It's still a very manual process. We had to think about how that at first we need to make a mold, so that's our mold right here, and then we lay our laminations down and we screw them down, and then we glue on the laminations in the next direction, and you can see us laying those laminations and we clamp them. So this is the version that we did where we glued it. We also did another version where we screwed it into place, where we screwed all the laminations together, and then we leave it to dry. So then the outcome are these panels, which are double curve panels. We're interested in how much bounce back we get in the panels, how much they come off the mold. So the mold is this shape, and how much do they move up? In this case, it was very little. In the case of where we screwed it, it was higher. They did more of the bounce back in those cases. And we both tested this in terms of, in this case here, you can see, you can kind of get an idea of the curvature. So this is a 10-meter curvature. It's actually, it would make a 10-meter span, but you can see I'm trying to get a picture of it so you can see the curvature, but it's not that curved because it's for a building, right? And so it's quite a large curvature. And then here we have what we did was, the first one we have a radius that's the same in this direction as it is in this direction. This one is a torus. It's the torus version, so it has a larger radius here than it does in this direction. So what we're interested in is doing a proof of concept that we can make basically any shape, right? That we can take something that goes like this, and we can reverse its curvature by changing the shape of the actual elements that go into that panel. So this is as far as we've done with this research here. The issue that we noticed was that every time you want to make a different curve, you have to make a different mold, right? And so that's the negative part of this, because if we want to make a free-form surface, we can calculate with our geometry. We can say, we need panels that look like this and panels that look like this, and we're going to cut them with our 3-axis machine, and we did an analysis. But then we need a mold for every single part, right? So the next challenge in this is, how do we do this without requiring a mold for every part, right? If we wanted to have a mold, this one mold, if we want to make a structure that's the same, right? That's an arch structure that's all the same, no problem, we can do this. The challenge comes when you want to vary that structure. So we can make a sphere, we can make a torus, and we can do it all with the same mold. So then the question is, what other molds do we need? And is there some way we could cut it so we could use the same mold but on 2 different sides? What are the potentials for that? Maybe we could glue something on each mold, I don't know. I'm sure architecture students could think about that for a while. But the other thing that we note is that this is not connected to anything else, because at this time we didn't have a robot. So we couldn't make a joint. We're like, we have this panel, but the 5-axis machine didn't have enough depth, right? So we need something that comes in at an angle to make a joint, right? And so that means that we need something that can do that. And so now we have a robot. We can now make the joints for these panels. We just need some more money. So That's the next, that's the torus panel, so the longer one. So the next part that I'm kind of interested in talking about is the idea of what's happening with robotics. So as we kind of started to push the envelope and looking at the geometry of the wood, you know, we started to kind of come up against this challenge that we didn't have enough axes, right? We wanted to make angles that we couldn't make. We wanted to connect pieces that were more freeform. So one of the potentials or the promises of the robotic fabrication is that we can go back to the traditional joints, and that we've lost the technology, as Anna was talking about. In Portugal, you lost the ability to make wood architecture, but also in Japan, although they still have some traditional joinery knowledge there. China, they completely lost all of their wood fabrication knowledge. And so these types of highly crafted joints are now once again possible whenever you have this advanced machining. There are, of course, aspects that if you use the robot, right, then you know that you can't make a square cut like that. So one of the things is that those would have to be round, right, because your bit that's moving in the machine is round. So they're not going to be the same, but it is potentially interesting to make a wood-to-wood connection again. Previously, when we deal with wood and connections, we always add steel, right? We're like, oh, okay, well, you know, we need to make a connection in wood, so let's add, you put but, and then you put them together and you put some steel in there, right? But that's not very sophisticated, right? This is much more sophisticated. And so this is also embedded within these are the ability to kind of change angles and take different types of loading. So when you put this together and then you start to pull on this, it's a tension connection, right? So I put these two pieces of wood together and it can slide this way, but it can't slide this way anymore, right? And it can't slide that way. So each one of these connections, also this one here, you put them together and then you put the pin in this way, right? And then again, you have this connection that can't slide this way and can't slide that way and also can't pull apart. This one here is more of a kind of connection that you can slide it in this way, right? But you can't pull it out like this. And so each joint is very specific to its to the forces that are on it, right? And that's a kind of a very interesting, to me, a very interesting architectural question. So no longer do we have this kind of dumb plate that we're putting pieces of wood together with, but its potential now we can put pieces of wood together in a much more sophisticated way. So we apply our robot, and then we have very interesting outcomes. And that brings me to kind of the last thing that I wanted to talk about, which is the robotic fabrication of wood and what you can possibly do with that. So this has been a kind of an area that I've been looking at in my studios for my architecture students for the last 3 years. And with those studios, I've been doing workshops. So at first we invited Institute for Computational Design to come and do the workshops, and now the people that we were working with there have graduated from those positions, and now they're working all in Canada. And so Oliver is now in Vancouver, David is at University of Waterloo, and I'm at UBC. So this year, it was just hosted at UBC. So these are the kind of the projects that we did in the last 3 years. What I like to do is kind of get my students to go through this process, because it helps them kind of understand what we call the machine space, right? So it was very interesting. I started the studio this year, and I was like, oh, okay, the students, you know, we always have this idea that students don't understand the materials they're working with, and they don't understand the machining processes. But when I started my studio, my students were, you know, they were assuming that they needed to make the wood go like this. And I'm like, you know, all those things you see out there, and you have the wood, and it's all kind of in a line, right? And they have different forms, but they've cut the plate into different shapes, and they've stacked it all together. And I'm like, this is very interesting, because it's not using all the axes, the 5-axis or the 6-axis or the 7-axis or the 8-axis that we have. It's only using 3 axes, and it's using flat plates, which meant to me the students had internalized the material and the fabrication processes that were readily available to them. So then I had to break the students mindset of having only those 3 axes, right? That you can move in the 4th axis, and you can kind of change the shape of the material. So I would no longer say that the students do not have an idea of what they're building or what their materials or their technologies are. I think, in fact, we do internalize the kind of the tools and the material that we actually work with. So I'm interested in, you know, part of the studio was to try and think about how we get the wood to go in rather than just in a flat plate in the plane, but we can make it go into different shapes. And so having many axes available to you helps with that process. It doesn't help so much with the material, because the material still comes mostly within the fabrication that we have available in terms of flat plates and dimensional lumber. But in my mind, that's only a matter of time, because once you can create custom engineered wood products, then you can start to kind of make your own wood product as you desire, right? Then we won't talk about that today. So these are the installations that have been done in the past, and I'm going to talk about the third one, which is what we call the double layered stressed skin structure. So this one was based on the structural idea of the stressed skin, which I think is a very clever idea, and it's used in such structures that are like this airplane, where you need a very light structure, right? So you're trying to keep the weight of the structure down to a minimum. In our case, it wasn't so much that we wanted a thin, light structure, because it's just sitting on the ground, but we needed to be able to curve the material, right? And so, as we did when we're looking at the barrel structures, at the structures with the double curved CLT, then in order to do that, we need a thin layer of wood in order to get the curvature that we want. So we don't have the option of making a big piece of wood, because we have to make it curved, right? So we certainly need a certain thinness to curve it. So how do you make a structure out of a curved structure out of a thin material? So we have these types of structures that are referred to. So the top one is the monocoque, mono being one, so one layer. That's a shell structure. And you can see that when you're looking at those kind of beautiful concrete shell structures, or even the ones that are made of masonry by Eladio Dieste. They're thin the thin shell structures. The problem is, if you do that in wood, you have a curve, but if you need to make the curve, you also need it to bend enough, so it's not strong enough to make the structure. So then the question is, then how do you create some depth, some strength within that element? And what we're looking for is depth, right, in order to be able to span. So the frame structure is the second one here, which is basically then you have a kind of a stiffer structure, and the exterior surface is not really participating as part of the structure. It's just kind of a skin on top of the structure. So what we were trying to look at here was the semi-monocoque structure, or a hybrid structure, where all the parts are participating in the structural system. So we have a top surface and we have a bottom surface that act as the flanges, and then the web are the vertical elements that are going in between. So we have a working bending member made of smaller structures that are all thin. So that, we thought, this is great. This is going to really give us some capability of bending. So this is what the structure is. This is the Grasshopper model, so it doesn't have any depth to it. But you can see what's happening here is we have these kind of multiple layers of elements that are lapping each other. And then we have the webs that are going in this direction. So we have the two flanges, and then we have the webs in this direction. And they lap each other and connect with these tabs. So that's the kind of the principle. And then in terms of structures, we're looking for something that will take some bending, right? And when we're looking at more the kind of the engineering side of it, we have, when we take some kind of element that's bending, we load it, then we have the base that's going into tension and the top that's going into compression. And so what we're looking at is something that will just will mostly take the forces in the tension and the compression and hold that planar. So the web is holding it planar and the flanges are taking the forces. So those are the two. We've put the material exactly where you need it to take those maximum forces. And then when we look at these, so this is what our structure is then doing, is we're looking at a whole bunch of webs and flanges, and the whole thing is kind of working together, and that way we can use many small elements instead of one large element, which is what we're kind of looking for here. So when we look at the kind of the rigid single curvature in this direction, what we need is something that's going to kind of make the double curvature. So we can make single curvature, but we're more interested in double curvature because it's harder, right? So we're like, okay, so in this direction we can cut plate to make that shape. In the other direction, then we have to bend it, right? And that's what the tabs are doing for us. The tabs in that lightweight plywood are actually doing the bending for us. So the other, I guess, maybe I can explain it in a little bit later, but so this actually works with any shape of structure, so that you can take a shell form, and you curve the shell form, you then duplicate the shell form, and then you divide it into as many divisions as you want. This is all scriptable. So in the Grasshopper, you can change the number of divisions, you can change the, you can change the curvature, you can change the offset. So it's a fully kind of modifiable structure. So these are, right now, these are cut with planes. So we're just, we're cutting them individually with planes that go through the structure like this. And that's perpendicular to the actual structure itself. So as we go through, we're cutting the geometry into planes. That will give us an ability to put our webs in straight. Because our webs are stiffer, they need to be kind of in a kind of single plane. And that's what's being identified in this part of the script. And then we take that and we can see then where our webs are going. So our webs are then developed from that. And then we lap our surfaces onto that. So these surfaces are lapped, and similar to kind of the second research project that we did, where we lapped the elements that went to make a curve. This is not so, this is not as much, you won't notice this as much, it's not using the principle so much, but each one of these plates is actually offset by the amount of the material so that we keep the accuracy of the model, right? So we didn't take one plane and then kind of, we took 50 planes for 50 different elements. And then each one of those planes is offset to the next one to keep them in the accuracy that you need to, because all of this is robotically cut. So it's within millimeters accuracy. So that's what's happening there. You can see the lapping of the planes as we continue here, which changes the curvature slightly, right? Because as we saw with the other research, you can actually make a curve with that. So that's our lapping surfaces then that are kind of superimposed on our webs. And we have the kind of information. You can see here what's happening is that we've drawn we're looking at each one of these as a strip that's coming down, and we have subdivided that strip into hundreds of points. Those are our points that are being tracked in terms of the geometry, and you'll see why in a minute. So we need to know exactly where, what the geometry of those points is, and then we offset those to determine the geometry of the cut surfaces. So you can see us then dividing that whenever we're looking at the element. And we decided that it would be really nice if we had a bench. So the other previous installations didn't have a bench. And it was like, the thing was, people would look at them and they'd go, oh yeah, that's interesting, but they didn't engage with it, right? It didn't make a space for people to occupy. So when you suggest that someone could sit there, then they go up and they sit on it, right? So this is a nice kind of enclosed area which has a bench to encourage people to kind of come up and then occupy it. So there's a part of it's developed with a bench. So if you're familiar with Grasshopper, this is just a graphing function that we made the shape of the bench with. So we just pulled we pulled the graphing function so you can change the shape of the bench. The other thing we have in a graphing function is how far that bench comes out. So in terms of like when it dissolves back into the structure. So you can see at this part of the structure, we don't have a bench, and that at a certain point it develops a bench. And that's all controlled with a graphing function. So we can tell it how many divisions we want the bench to be, and then it kind of drafts it into the surface. So again, it's all controlled on those parametric functions. And so in this case here, then we're looking at how do we make the shape. So you can see there's a requirement for bending for the plywood. So the plywood now, the webs are stiff, and the plywood, which is what's being shown here, is bending. So we needed to do a curvature analysis to see what the natural bending radius of the plywood is versus what we have here. So if we know the plywood can bend in its elastic range without breaking a certain amount, then we need to analyze the curvature at each point to make sure that it can still bend. So obviously there's a problem here, right? Because we have this bench. And the bench doesn't, the curvature, so we're using relative, like, the plywood, it comes along, and then when it needs to make the bench, it doesn't have enough bending capacity. So we said, okay, that's fine. We're just going to kerf it, right? So in this case, we kerfed the bench. Does everyone understand what I'm talking about by kerfing, maybe? I can maybe show you a picture here. Sorry. There's kerfing. So I'm giving it away. But that's the kerfing part here, where we're cutting the wood and making it weaker on purpose in order to kind of make that bench capacity. So we'll talk more about that. But let me go back. So there's our bench there that's coming out, and you can see that in this case here, we have to modify the tabs, right, to make that bench happen. So where we're looking at where we want the bench, we say, okay, I want a bench there, so I don't want to have a back, so people have to be able to sit on it. So I'm going to kind of modify my script. So we say, in this particular area where you have this bench from the start to the finish, then you're going to make an extra large tab, and then that tab is going to kind of smooth its way back into the structure. So that's what we're doing in terms of what the parametrics are doing. We also want to kind of keep this. We want to keep control of the spacing between the panels. So within this kind of script, we have these elements that are happening consistently with a consistent width, and we're cutting those out of the plywood. And then you'll see that there's a bigger gap on this side than there is on this side. On this side, it overlaps. So at certain points, then you want your structure to open up, light. At certain points, you want it to close down. So that's controlled again on a mapping function to open up the spacing between the elements at certain points and to close it down at certain points. So again, there's a kind of a complexity within this script to allow that where it overlaps and where it doesn't. And in this case, we're keeping the tab spacing the same and allowing that kind of opening to happen in different locations. But if anyone ever tried to use the unroll function in Grasshopper, in Rhino, you'll realize that there's a limitation on that function. So when we are thinking about what we're doing in terms of making the model and what we're doing in terms of using the robot, to use the robot, we want to take those strips that are curved like this and we want to lay them flat, right? So what we did is we said, okay, we call the unroll function. So we say we have something curved like this, and we just say, okay, lay it flat. So I want exactly the same geometry that I have here, and I want it flat. And you look at this and you're like, well, this doesn't have the tabs. Like, there's no tabs on this. Because the unroll function in Rhino is not sophisticated enough to pull that geometry with it. So we go back and we take the base information of these points, right? So these are just plain offset points, and then you can unroll that. And then we go back and superimpose all of that geometric calculation, which is a lateral movement of those points along the geometry of the line. So we just say, okay, we want you to move out that direction there, and that makes your tabs again. So in the geometry that's like this, we simplify it, we unroll it, and then we add again the complexity, which we already have in the script. And that's a kind of it's a function right now of the complexity, the relative complexity of how that script is working. But in the end, this is what you get. See these little numbers on the bottom? These are very important. Because when you get to the point where you fabricate everything, every piece is different. So you will never be able to kind of keep track of the pieces if you don't number them correctly when they come off the robot. So always pay attention to what you've cut and put the number on it immediately when it's on the bed before it comes off the bed. We did, and invariably you'll some you don't know where it goes, but that's just part of it. So this is what it looks like then when you unroll it, and that's what we cut in terms of with our robot. So then we have to put it back again. So that's our looks like when we actually ended up building it, and the elements of the kerfing you can see there relatively. It's not very delicate kerfing, right? This could be a whole study on its own. So what the reason that it's not very delicate is because we have 2 bits. We have a tool changer on our robot, and it has 2 bits. So we have a cutting bit, and we have a drilling bit. So we needed the drill to do the rivet holes, and we needed we need the cutting bit to cut the outside. So that doesn't leave us any other cutting bit that we could do the kerfing with. So when we put down the piece and we cut around the outside of it, right, then whenever you go to change the bit, right, then you end up with an inaccuracy to change. If you have the 2 bits that are the tool change, and then you decide to go back and take another one, you'd have to take it out of the robot, put the new one in, and then you'd have to figure out where the 0, 0 was on that new bit. So that would, if we wanted to have really good kerfing, we either need another bit on our tool changer, or we would have to go through this whole process every single time we cut a panel, right? So that would take too long. So what we did was we just said, okay, we're going to have a very kind of unelegant kerf using the cutting bit. So that's why our kerfing is not as ideal. The other thing that we could do if we had enough time is to say, okay, I want it to curve more, so I'm going to kerf more in the higher curvature areas and kerf less in the lower curvature areas, and tune your kerfing to the curvature, right? Again, that didn't happen here, but it's another kind of way of making wood curve, right? So just in case you guys want to do that, I hope you do. So anyways, this was just us studying the model, because what happened was we had in the workshop, what we wanted the students to be able to do is to be able to all cut their own versions. So part of the way that we work the workshop is we take the script that is written, and then it's a totally malleable script. You can subdivide it different ways. You can pull your bench out at different ways. You can put in different surfaces. So it's just a base script for a stressed skin structure, and then that structure can be applied to basically anything. So the students could all make their own structure then, if they wanted to. And then we had Stuart, who's on the right-hand side there. He's one of our former students who now works at the company that got bought by Katera, that I was telling you about the startup. So they've bought our robot programmer, but anyways. So he made a script that could change it from a script that cuts wood to a script that cuts paper so that everyone could make a model. But the problem is with these models, and we've tried to do this several times and it doesn't work, is because every single piece of that model has to be put together the same as the piece that we're making in the full scale. So it takes as long to make the model as it does to make the full scale. So everyone didn't want to spend all that time making their models. So we had one model made of the kind of what I call the prototype geometry. So that's that. So then you can see us here. So it looks very small in the model. You see how small it looks, but then it looks very big when you actually go to build it. We're like, whoa, what have we done? So this is us trying to think about how we're going to put this thing together. So we use, in the most of these prototypes, we use a base structure that helps us kind of space each element well until the rest of the elements are put in. So once the top elements are put in, then everything is perfectly spaced because everything is perfectly cut. But we have these kind of large pieces that are hanging out in space that we have nothing to place them in relative to each other, so we use this kind of base structure. And in this case, we cut the base structure in certain locations. You can see a joint there, and then that's how we delivered it to site. So this is us. This is one of our students here operating the robot. So when we run the workshops, we try everyone takes the script for a certain piece and then takes it, puts it in the robot, runs the code, and then so that they understand the kind of the workflow between how you work in Grasshopper and then how you get that into the robot. So the whole point of the workshop is to accelerate understanding of that process, the way you go from a kind of a complex script to a built form. It's in the studio. In the studio, all the students are developing their own designs for a design problem that I would give them. But you know, to get to the point where you can actually make an output, which you have the information, because you see how you have to manipulate all of those points very accurately to get the robot script for the pieces. So obviously in a normal studio, you don't have an ability to have the time to do that. So we're trying to take the students' experience and accelerate it quickly by already giving them the script and then saying, okay, now you take that piece out of the script, you put it in the robot, you cut it in the robot, and then we all put it together. And so that kind of hopefully then gives a broader kind of intuitive understanding of the robot, because once you realize, okay, that angle is going like this, and that's what I can do with this, and this is how the material works, but that doesn't work. And then when I go and put it together, I have to think about the sequence that I'm going to put this in, because if it's lapping like this, and the other side is lapping like that, I can't put it together, except, in a very particular sequence. So all of that process of using the tool and then looking at how it works, understanding the scripting, putting it together in the physical form, I think it gives the students a better idea of how they design. So when they went back to their designs, then they were like, oh, actually, I have to change it because I understand that the machine, is working to do an undercut here. If I put the piece down like this and I want to do a cut like this, and then I want to do a cut like this, then I have to flip my material over. So that machine time starts to play a role. And when the students have to stand there waiting for the machine to cut this thing for 20 minutes, then they're like, I don't want it to cut the other side, because I'd have to then take the piece. By the time I flip each piece over and then run a script for the other piece, that's tripled the time of the machine time that I would need for making that piece. So then the students start to think about how they might design because of the tool that they're using, right? And also machine time, because machine time doesn't seem very significant when you're in a studio trying to make up a design, but when you actually get out there and you're having to wait for this machine, and we had 3 days to make this project, right? So we can only use the robot basically for 16 hours. So the number of pieces in that is actually determined by how many hours we had for machine time. Because we knew our workshop was only a specific number of days, right? So the cost of structure is going to be related to your machine time and the amount of material you have, right? And is also going to be related to labor. So in this one, what we found was it went together very quickly because we had all the information for how it should go together within the rivet holes, actually, right? They had to overlap. They were overlapped and put in very precisely. In the previous year, we had some parts that we had to measure and put on, right? And so the amount of time that it takes to measure something on site and to place it is like about 5 times the amount of time it takes to line up 2 rivet holes, right? And so you start to kind of understand also when you're designing that you want to have some element in there that tells you how one piece fits to the other one. When we're looking at that kind of very precise lapped structure, like this, right? You can see people, they're putting these things are lining up. So not only we have these tabs, right, that are going in, and then we have these rivets. So the tabs are keeping the elements straight onto those things like that. So they're positioning it like this, and the rivets are positioning like this. And so then we know how to put that on. If we tried to measure each one of those things, can you imagine how long that would take? Because this is 2 millimeters, that's 3, that's 4, that's 5, that's 7, that's 9. So that is going to take a very long time just to measure those kind of elements. So not only does the robot give you the ability to put something together very precisely, but it also gives you the ability to cut down on the time that the laborer takes to do the work, right? And so that's a very significant cost in terms of how your construction process goes. I know we don't talk about cost in architecture school, but trust me, you'll talk about it a lot when you get out. So these are the three panels that we put together. You can see here, when you look at this part here, you can see the spacing of them increasing, and then we can see the spacing of them coming together and then turning the corner like that. The geometry of this structure was arranged so that it has a depth, so that it can't overturn, right? So that when the wind blows, that it's not in one straight line, so it has this depth, and so if it overturn, then it's stabilized both in this direction and also in this direction. So the overall global geometry is also participating in the structure itself. And this is our campus. So David took this beautiful picture, framed by our waterfall at our center. This is placed in the center of the campus because the campus likes our projects, so they let us have a very prominent place. And they even let us have it this year, so we got word 2 days ago that we got our funding to do this next installation. So we put it on campus, we let it sit there for a year, and then we take it down with a chainsaw and build a new one. So this will be destroyed probably in September. But if you come before that, you can see it. So please come and visit. And it's also marine grade plywood, which is why it can sit there for so long. Because as you know, when you're trying to leave traditional wood out, it's very rainy in Vancouver, and the wood will degrade. So we use a marine grade plywood, and then also use a varnish on top of that to try and give it a little bit more longevity. But after 9 months, the last one was looking pretty. You know, it wasn't looking so pretty anymore. It was still fine, but we're anticipating the same thing will happen in this one. So that's our final structure. When you look at the back of it, it looks quite different. So that's the back view of the structure. You can see. Well, I mean, now that I've told you all about the coding, you can see the code right in the built form. So all of because the points are, all those gradients are lining up, you can see the kind of the way that the elements kind of transition down the wall. So the top part is also divided in the same number as this part here. So all of the elements that are transitioning are transitioning along those tracking lines that we set up. And then this is the kind of the other view from this. So we oriented it on campus so that this is the view from when I'm walking this way, right? And the view I just showed you is from where I'm walking in the other direction. So depending on what direction you're coming from, this one is coming down this path, and this one's coming down the other path. So this is inviting you to go and have a seat. We also have this, you see this circle at the bottom. This was me optimistically thinking that we could light it from the inside. So I was like, yes, this time we're going to have lighting, because the last 2 times the problem is that the lights on campus, you know, are missing the structure, right? So at night, it's like the light is over here and the structure is here. So we got the campus landscape architect to change the lighting. And we were going to try and light it from the inside, but they couldn't get any power to the site. Because I don't know why, but anyways, they couldn't. So it's still potential, but it's not lit. And there's a squirrel. We had a discussion of squirrels the other day. All right, and that's our kerfing, as I showed you before. And then this is our kind of very precise lapping of the structure. And I think that's all. So thank you very much. Do you want me to take questions, Anna? Oh, lots of questions, yeah. And you can, if you can't say them in English, I'm sure you can translate them for me. Yeah. A way of making. In general, for the wood, I can answer the first question. Right, it's a marine grade plywood. So marine grade is it's so that it can stay out in the water. It still will degrade over time, but it's a better type of plywood that to be exposed to the air, to the water. And so that's the kind we use for this. And that's just, we can only get it in certain sizes of panels. We would have liked to have a 16-foot plywood, because that way, because if you notice it gets very tall, right, at some point it goes above the 12 feet, so we wanted a 16-foot, but it doesn't come in 16-foot plywood. Some of the plywood you can get, but not that one. And so, so we had to use the 12-foot, and you can, there's a, I don't know if you guys can see the other joint that we put in, because we couldn't get our plywood that long. Let me just see if I can find it for you. I think I saw it in this picture here. Right in the middle, you can see there's a puzzle. You see that right in the middle here, where the wood changes color? That's because our plywood was not long enough, so we needed to joint it somewhere. So that you can see that all the way. If you look carefully, you can see it all the way through the element. So, but it wasn't. We didn't have a choice of material because we wanted to leave it outside in Vancouver in the rain. We are going to one of our next projects is to do an installation using Akoya. You guys know Akoya. It's a wood that can leave, they've treated it as acetylated wood that you can leave outside. And then we're going to do a project with that one to demonstrate it. And that one will be able to stay permanently. It will be a social bench, so a bench with a roof. But that's another challenge because it's dimensional lumber. So all the curvature you see in these projects is done by plywood because we're bending it. So we're cutting it, it's a very thin wood. So when we have a dimensional lumber, we can't bend it so easily without cutting it. And so that'll be another challenge because I'm interested in seeing how I can make dimensional lumber, make into a double curved surface. So we'll see what happens with that. And then in terms of the foundations, these ones here, this does not meet code because we put a base plate of wood on top of the ground, actually. And the way we anchor it is we use just rebar, and we go in from the sides and we tighten, we bang the rebar in and then screw on a bolt. So we kind of tension it down to the ground in two directions. But in Canada, we always have to take the wood 6 inches off the ground so that it doesn't get wet and weather. Piles sometimes, if you think about piles in the water and they're treated, then you can use them. But the problem is where they get wet and dry, right? And then the wood degrades. So I don't know of an application using wood for foundations in a permanent building. When they use Akoya, I'm pretty sure you could use that in do you guys know any wood foundations? Lisbon, oh yes. In the old town, yeah. Do they allow that now? No, yeah. But with the Akoya wood, perhaps they will allow it again because it doesn't degrade, I don't know. Yeah? Yeah.
There is a bridge that stops the river. The bridge crosses the river. It's made of plates of Akoya, and it's there.
Yeah. And do they foundations are also Akoya?
Yeah, I think so. It's like really long.
Yeah. And that's a very exciting product, I think. It's a very exciting whenever you can think about wood being left outside, right, without having to be protected. Because one of the features that you always see in Vancouver, and I think all the projects I showed you are probably showing you from the inside, because the outside has to be clad, right, to protect the wood. And so there's this kind of this lack of, if you have an overhang or you can see into the building through glass, then you see the wood. But many times but you just can't leave it outside. So I'm very excited about this new potential of being able to kind of leave wood out. And I'm waiting for them to make plywood. So, yeah.
First of all, congratulations for the research.
Thank you.
Regarding the projects you've shown, I've noticed that most of them pursue curvature.
Yes. That's my interest, yes, in these particular projects.
The title of the presentation talks about the language. So my question is, why do you think that the future
Because it's difficult, right? Because wood, we know how to make wood go in a straight line, right? We know how to make it linear and we know how to make it planar. But in terms of making it curved, that's one area. Like I said, you can machine it, but then you waste a lot of it. And so that's why I'm interested in the curvature, so that it's not that we don't do straight lines. It's just that if you wanted to do something that wasn't a straight line, that you could. I think that's why my interest has been in curvature in these particular experiments. The ones that we did with the kind of the lapping in the first set of experiments and the folded plates, they were more linear, but also being able to make a kind of a global curved geometry. But I think it's mainly just because the other stuff we already know how to do. Yeah. But the surface structures that we were looking at are, even the ones that were planar, we tend to not think of wood as a surface structure. We tend to think of it as a hierarchical thing that's made of smaller elements. So surface structures, I think, are definitely, one of the aspects that would be planar, but would be kind of part of the new language, I think. I think it's important to, I guess, present architecture students with potential for doing something other than what we think of as a traditional structure. Traditional structures are, of course, you can take variations on that and put angles and things like that, but I think connecting the parametric and the kind of the new digital processes to the wood design really helps kind of excite people about what you could potentially do. So that's another reason why I like to present those projects. Yeah.
About the software,
Mm-hmm.
is needed to keep up with the innovation. Does the university helps the students to learn that software, or is it a concern of the university?
We talk about it all the time. It's always talking about the software. So, and we teach tutorials for the students, and it's generally other students that teach the tutorials, right? So what I teach the studios, I have a teaching assistant who's an expert in Grasshopper, who troubleshoots the software. So what happens, Stuart, who you saw in the picture, he was my teaching assistant from the year before. So he's an expert in Grasshopper. And so the students come into my studio and they have done training, not all of them, but about half of them in Grasshopper. So some of them are starting from scratch. They know how to 3D model, but they don't know how to use the parametric software. So I first send them to the internet, to lynda.com or to and I tell them, do some basic tutorials, right, on understanding how the components work and things like that. And then Stuart, or the TA, teaches some basic things. And then when they start to script, the problem is with the scripting is that every time you do something, it's something different than you did before. So even if you know it, it's like, or there's a different way of doing it, because you can do it in about 10 different ways. Like I might do it differently than you, that might do it differently than Anna. So even given the same problem, we could do it in different ways, which is great, but it also means that if you teach one particular thing, it doesn't mean the person knows the software. So the way that I find most effective, having taught this now for many years, is that I have the person who supports, and because I can teach the Grasshopper and support the students, but what they need is someone who's when they're on studio at 11 o'clock at night to help them, because they get stuck on one particular aspect of that script, right? And so the TAs that are supporting are usually the people who are always in studio and who are supporting the students, and they then look at the script in great detail to see what the problem is, because that will sometimes take a couple of hours to go through the script and figure out what the problems are. So I think you need someone who, when you're learning the scripting in the early stages, if you want the students to progress quickly, then you need a specialized troubleshooting help. So I beg my director for extra TA support. Usually we don't have TA support for studios, but I'm like, please, the students would have a better learning experience if they have this technical support. And so I bring that in for the students. So that's how we deal with it. But it's a very good question, because it's a very big issue. And I always, just in general, when it comes to software, it's like whenever I do a project, often I'm using a different software than I did before. So I kind of think of software like modeling materials. Every time you do a model, you think about what material am I going to use? What would be the best to express what I want to do? Same thing with software. So you don't use the same software all the time. You might think about, I want to do this particular thing. What kind of software do I use? I think that it's just a fluency with learning software where you get kind of comfortable and you say, oh, I know how to learn a software. I know this CAD program. I can learn that CAD program. You know, and so if you take that kind of open attitude towards the software, then it's more of a kind of, I think, a flexible tool for an architect than being kind of, you know, in one particular thing. Mm-hmm. Okay, thank you. Thank you, Anna. Thank you. Thank you very much.
Very, very nice class.
Yeah. No.
You can't.